Alright, hi ladies. We're going to continue on with our electron configuration. We're going to use the example of carbon. If you look on the periodic table, the atomic number of carbon is 6, and that means that there are 6 protons, and the number of protons has to equal the number of electrons in order for the atom to be neutral. So when we look at electron configurations, we're trying to map out the address for those 6 electrons. Okay, so you guys have your diagram. Let's look at the rules. Aufbau's rule says you have to do lowest energy level first. That means energy level 1 is lower than energy level 2. S sub energy level is lower than a P sub energy level. So as we map out the electrons, you guys can use the diagrams to help you, but 1 has a lower energy than 2. 2 has a lower energy than 3. Those are our principal energy numbers. S sub energy, which has 1 orbital, is lower energy than a P sub energy level, which has 3 orbitals. And P is lower than a D sub energy level, which has 5, and D is lower than an F sub energy level that has 7. And you can see the notes that we were taking the other day to verify that. Okay, so Aufbau's rule is you fill its lowest energies first. If we look at carbon and we have 6 electrons and we want to get that address for those 6 electrons, the idea is that we're going to put lines in each circle to represent electrons. A single line means 1 electron. I write it in one direction to show that the electron spins in a very specific direction, knowing that when I cross it with the other line for another electron, an X means 2 electrons per subenergy level. And Pauli exclusion says no more than 2 electrons in an orbital. Okay. The opposite spin is just something to remember that electrons repel each other, and that's a way that they can handle occupying a close space with one another. So if I'm trying to map out 6 electrons for carbon, I'm going to put 1 in the 1s, 2 in the 1s. This is filled. I'm going to move to the next energy, which is 2s. I'm going to put 3, 4. Now my 2s is filled. I'm going to move to the next energy level. Per Hund's rule, I can't put a second electron in this orbital until each orbital has 1 electron. So for right now, I've got 2, 4, and if I want 6, I only have 2 more electrons left. So I have 2, 4, and then 1 electron in each of the p orbital, 2 p orbitals, but I do not have another electron for that 3rd orbital. So how I would write the address or the electron configuration would be 1s, and there's 2 electrons, 2s2 with 2 electrons. In the 2p energy level, I only have 2 electrons, so I'm going to write a 2 there. 1, 2, 2, these are my energy levels. We're going to correspond those in just a minute to rows on a periodic table. S and P are my orbitals and my subenergy levels. They tell me where the electrons are going to go. And then the 2's, in this case, are the number of electrons in each. And when you add them all up, you should get the total number of electrons for whatever element you're trying to map out. Okay? So you guys have these diagrams. You can use these diagrams, and then you'll have to be able to write the electron configuration out even after you've used that diagram. That diagram is just a way to help you to manage all the different rules and the knowing which energy level is which. Okay. Now, we're going to go to the periodic table for a second. What's nice about the periodic table, the one that you are getting in class, this is meant to be a template, really. It has all the elements in all the correct places, but it doesn't have any columns. It doesn't have any extra information to label of the columns or the rows, and so this is going to be a really good tool for us so that you can actually see, how the periodic table is organized for electrons, because ultimately this comes back to the idea that, if you remember, each column, right, up and down, each column is a family, it's a group. It has something that it's similar to. They're related in some way. And in this case, with the electron configurations, and the idea that we're doing here is they all actually have the ending of the energy, the sub-energy level, and the number of electrons in that sub-energy level are the same in elements in the same column. And so that tells us a bit about its chemical reactivity. Lithium and hydrogen and sodium and potassium, we had originally written on our other periodic table +1. And that's to say, well, they lose one electron. So if you lose a negative, you become positive. Well, they chemically behave very similar, and so their electron configurations are also going to be similar. So we're going to color this up and show you what we're talking about. If we go to the PowerPoint, you'll see here a completed version. So groups 1 and 2, columns 1 and 2 are my S block, meaning whatever I'm ending on would be my S block. Groups transition metals are going to be my D block. So if you count them, it'd be D1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just so you know, there's 5 orbitals with 2 electrons. You can put a total of 10 electrons in there. And then we've got our P block, right? There's 3 orbitals, 2 electrons in each orbital. P1, 2, 3, 4, 5, 6. And then our F block is the 2 rows that get pulled out of the periodic table on the bottom. If you counted all the boxes across, it'd be 14. There's 7 orbitals in the F. 2 electrons in each orbital would be 2, 4, 6, 8, all the way up to 14. Okay. You'll notice that the rows become my principal energy levels. So if you're in row 1 at the top, you're energy level 1. If you're row 2, you're energy level 2, 3, 4, and then you'll see that the D blocks are labeled different because we say that the D sub-energy level starts in energy level 3. So the D gets a little offset from the S and the P. So that's something to label and to watch for. Likewise, the F being pulled out, F sub-energy level starts in energy level 4, and you could do 4 and 5 for that one. Okay. So let's go back to our periodic table. And let's start labeling them. Okay. So if you did the electron configuration for hydrogen, you would realize it has 1 electron. So if you looked and you tempted it on your diagram, you would have a 1s1 electron configuration. 1 coming from the first energy level because it's in the first row, reading top to bottom. S, because this block here is my S1 and my S2. So this becomes an S with 1 electron. The second column becomes a filled S sub-energy level with 2 electrons. So this is our S. I'm going to highlight that. Because helium's kind of goofy, it also is a part of this. This helium could really be transposed here, just so you know. It can be moved over there, and it would be a 1s2 electron configuration because there's 2 electrons. Okay? All right, so if I wanted to label all my energy levels here, lithium, if you realize with 3 electrons, we would start at 1s, and then we would go to 2s. So if I put 2 electrons in 1s, lithium having 3 electrons would be 2s1, which makes sense because it's 2s1. Beryllium would be 2s2. So what we're trying to do is create a grid, so basically you can just read across and down to verify what would be the ending point for your electron configuration. Sodium will end in a 3s1, magnesium will end in a 3s2. Potassium a 4s1, a calcium, a 4s2. Note that hydrogen, lithium, sodium, potassium, rubidium all lose 1 electron. Their overall charge would be a +1 from the loss of that 1 electron. And so this is just giving us a little bit of an insight into why they behave that way. It's that 1s electron that's kind of hanging out, not attached to anything else, and so it's easy for those elements to lose that 1 electron. Okay, so if you label your rows across, you should go 1, 2, 3, 4, 5, 6, all the way to 7. You have this periodic table, so that is how you should also label it. If we wanted to do the next one, we're going to highlight this whole group here. And we'll just do this. We won't worry about element 114 because those are man-made and we don't talk about those very much, okay? This is going to be your P block. Okay. So if you look, you would have your P1. Oops. Want to make my colors look nice. And I recommend that you take different colors so that you can see your carbon family, right, column is going to be P2. Your nitrogen column is going to be P3. Your oxygen's P4. Your fluorine's P5. And a filled P sub-energy level is your noble gases. And that's key here. Filling your P sub-energy level gets you that stability. And that's what we're going to look like in terms of non-reactive or unreactive substances. They have that filled P sub-energy level. Okay? The energy levels are the same as they are for the S block. So 1 would be over here for helium, but then we're going to do 2 for boron, because if you go directly across from lithium, 3, 4, boron's 5, it's still the second energy level. P starts in the second energy level. P does not start in the first energy level. It goes S in the first energy level, P in the second energy level, D in the third energy level, and F in the 4. Okay, so I can just go down and I can number these so that I know what energy level I have for each row in the periodic table. So hypothetically, if I were to take aluminum, aluminum would end in a 3p1. So if I mapped out all the electrons, there's 13 of them, it would be 3p1. And ultimately, I could just work backwards then. From there, I would have 3s2, 2p6 is filled, 2s2 is filled, 1s2 is filled. So this is for aluminum. I'm going to erase this so this doesn't get confusing. Okay, and so I'm going to work backwards using this method, and then I can just look at the periodic table and know right away where I'm ending, and then I just go back and I check what's been filled in. Okay, so that's the P. We're going to get into the D here quick. D is this block here in the middle, and if you label the D, you will see that going from 20 to 21, we have D1, D2, vanadium's D3, chromium's D4, manganese is D5, 6, cobalt's D7, nickel's D8, copper's D9, and zinc family is D10. Okay, and then that is my D block, and then lastly, you'll have your F block. And if you go through and you label those, you'll start with lanthanum, F1, oops, F2, I don't know why I want to keep doing D, F3, F4, F5, all the way to the end, you would have F14. So you should fill all these in. And feel free to re-watch this to make sure that you can check that all of them match up with the right column.